Okay, well, welcome everyone to June's Machine Learning for Land Modeling seminar, or ML4LM. I'm John Cranko-Page, and I'll be sort of chairing or hosting our talk today, where we have the pleasure of welcoming Dr. Patricia de Rosnay to give us our talk. Patricia is a principal scientist at ECMWF, where since 2016 she has led the coupled assimilation team. Patricia and her team are heavily involved in the development of ECMWF's integrated forecasting system and artificial intelligence forecasting system, maybe better known as IFS and AIFS. Some of her select advancements include work on the assimilation of soil moisture using EKFs and snow data via a two-dimensional optimum interpolation scheme. Patricia has also coordinated the ECMWF contributions to multiple ESA and EU METSAT and EU projects, including the Horizon Europe Copernicus Climate Change Service Evolution Project. Dr. de Rosnay earned her PhD from the Université Pierre et Marie Curie in Paris, and she worked on the Orchidee LSM at, forgive my pronunciation, Laboratoire de Météorologie Dynamique, before moving to the French National Centre for Scientific Research, CNRS. She joined ECMWF in 2007 on secondment from CNRS and has been at ECMWF ever since. So today, Patricia will be talking to us about improving and maximizing the use of land surface observations in weather forecasting, particularly through the application of machine learning. So please join me in welcoming Dr. Patricia to the ML4LM webinars. And we have the Q&A open, so you can post questions in there, and you should be able to upvote other questions that you would like to see answered preferentially. You can also raise your hand, and I can unmute you at the end once we get through to the end of the presentation and the Q&A section, whichever you prefer. But for now, I'll hand over to Patricia, and hopefully we're in for a fascinating presentation. So thank you, Patricia.
Thank you very much, John, for the introduction. And yeah, indeed, I'm going to talk about our activities at ECMWF to enhance the land surface data exploitation using machine learning for weather prediction systems, but also for reanalysis applications. And first of all, I want to acknowledge the contributions from many people across the different teams at ECMWF. I'm leading a coupled assimilation team, but we are working very closely with other teams at ECMWF. So for numerical weather prediction, we use an Earth system model. And I like to show this picture from Kevin Tranber's 2007 because it really shows that land surfaces are complex compared to other components of the Earth system. And we represent in our NWP, numerical weather prediction system, we represent land surfaces. We have a land surface model, which is called ECLand, where we take into account various processes at the land surface. And a very striking number is that globally over land surfaces, 2/3 of the precipitation is coming from land evapotranspiration. So it really shows the importance of having a correct representation of the land surface processes in NWP systems to get the atmospheric forecast right. It's only one of the examples of the importance of the land surface. We also account for other components, ocean and sea ice, illustrated here, and the interactions between these different components. And ongoing activities are on coupling with hydrology, but I'm not going to cover this today. So Earth system model means that we need an Earth system data assimilation because for weather prediction, we need to provide initial conditions to each prognostic variable of the forecast model. So when the land surface model team, Swale and others are developing the land surface model, we need to work together so that we make sure that we provide consistent initialization of the land surface variables. And with a coupled Earth system modeling approach, we need to develop a coupled data assimilation approach to have consistency across the different components. And as you see on the illustration on the right, we use a different data assimilation methodology. For the atmosphere, we use 4DVAR. For the land surfaces, we use a simplified extended Kalman filter for ocean and sea ice 3D VAR, and for the waves, 2D OI. So we use a different data assimilation system because there are different constraints and requirements for each land surface, for each component. So our coupled data assimilation strategy is described in several papers listed here. And one of them, it's a newsletter article just published today at ECMWF website describing stronger coupled land atmosphere development that we did. So coupled assimilation, as I said before, the objective is to have consistency across the different components. It means that we want the atmospheric data assimilation system and the land data assimilation system to communicate within the data assimilation window to exchange information. So the objective is really to provide balanced initial conditions across the forecast model components. We want them to be in agreement and so that there is no initialization shock in the forecast. It's also a very good opportunity to enhance the exploitation of the surface-sensitive satellite observations. Currently, in our NWP system, we completely underexploit satellite observations, which are sensitive to the surface. We use loads of satellites for the atmosphere, but in the end, I will come back to this later, for the land surfaces, we don't use that much. We use a bit for soil moisture and for snow initialization. And we don't use much because there are big challenges, again related to the complexity of the land surfaces, both on the land surface modeling side, but also on the radiative transfer side. If we want to use satellite observations, we need to have a radiative transfer model, and this is very difficult to have good performance over such complex surfaces. So we are increasingly relying on machine learning approaches to link level 1 satellite observations to land surface variables in our system. So we use and we develop the usage of existing missions, so ASCAT and SMOS, Sentinel-P for SIF observations, HydroGNSS. We are also preparing for future missions, well, Crystal, mainly for sea ice activities, LSTM, and Simmer on the right. So what do we do currently for operational NWP? For soil moisture assimilation, we assimilate at the top, you see in the title that we use 2-meter temperature, relative humidity, which are screen level observations, which provide a very good proxy for soil moisture. So we use these in situ sign-up observations, but in addition to that, we use satellite data from ASCAT, which is an active C-band microwave sensor. It's a EUMETSAT mission, which is operational, and it was initially designed for ocean surface wind, but very early in the 90s with ERS, the ERS mission at C-band as well. It was demonstrated by a group in Vienna, by the group of Wolfgang Wagner, that ASCAT backscattering coefficients at C-band were very relevant to monitor soil moisture. And we implemented ASCAT soil moisture assimilation more than 15 years ago. And it's been used in ERA 5, and it's going to be used in ERA 6 as well. We also use SMOS. So SMOS is an ESA, European Space Agency mission. At L-band, it's a passive microwave mission. And in contrast to ASCAT, which was designed for ocean wind, SMOS was really designed for soil moisture measurements from space. And we've been assimilating SMOS in operations for NWP since 2019. And SMOS will be used for the first time. It's being used for the first time in a reanalysis, global reanalysis in ERA 6, which is currently in production. And we also use SMAP as part of our operational monitoring system. It is completely implemented in the integrated forecasting system just for monitoring so that we compute the departure statistics compared to our model fields. So this slide is to illustrate the overall impact of the soil analysis for numerical weather prediction. So we have a unified soil analysis approach where we, in the simplified extended Kalman filter, we analyze soil moisture and soil temperature as well as snow temperature. But here we focus on the impact on soil moisture and soil temperature. So we did some experiments. We have a control experiment, which is a reference line. On the right, this is for the northern hemisphere. It shows the difference in normalized root mean square error for 2-meter temperature forecast for different lead times, the x-axis, 0 to 10 days. And it shows, compared to a reference, which is our operational configuration, it shows the degradation in 2-meter temperature forecast for different lead times when we switch off the soil analysis. So no SCKF soil analysis means that we increase the 2-meter temperature forecast errors by almost 14% in the very short range. And the degradation when we switch off the soil analysis is significant in the northern hemisphere extratropics until day 8. So it's a very substantial impact of the soil analysis for NWP. And in the tropics, the impact is around 12% in the short range, but it remains significant for the full medium range until day 10. While in the southern hemisphere extratropics, well, you know that we have less continental surfaces, but despite of this, we have a very significant impact up to day 3 and still quite strong day 4. So overall, soil analysis is super important for NWP, but I think I don't have to convince this group that it is the case. And related to SMOS, so I mentioned that we've been simulating SMOS since 2019. And the first implementation that we did for SMOS data assimilation was using a neural network illustrated on the top left. So what we do for SMOS, we receive the brightness temperatures in real time, which is great because SMOS is an Earth Explorer mission, but the European Space Agency has immediately made available the product, the SMOS brightness temperature level 1 in real time, so that we started at the very early stage of the SMOS mission to develop the infrastructure and algorithm to assimilate SMOS. And so we developed a neural network to retrieve soil moisture from SMOS brightness temperature that we receive in real time. And this neural network was trained on our soil moisture so that it was implicitly bias corrected and could be assimilated directly. So we've been using this from 2019 until 2025. And last year, 2025, well, in fact, in November 24, we had a land surface model upgrade with IFS cycle 49R1. It was a big model upgrade because the vegetation maps were updated. And we also introduced some changes in the land data assimilation system. So these were good motivations to retrain the algorithm to retrieve some moisture from SMOS brightness temperatures. And we did this with XGBoost. It was done by Kirsti Salonen. And on the right, you can see an information content analysis showing that the brightness temperature is really important to take into account along with the geolocation and vegetation type information to retrieve soil moisture. And on the left, you see the performance of the retrieval with the y-axis showing the XGBoost soil moisture retrieved from SMOS versus the model soil moisture with good retrieval performances. So this is what we've been assimilating for operational NWP since February last year. And this slide illustrates the impact against completely independent observations. On the left, it is against diverse surface observations, including the sign-up 2-meter temperature and humidity observations. And on the right, against radiation temperatures. And it shows the background, the first gas departure standard deviation. So everything on the left of the vertical line, which is a reference operational system without SMOS, shows that when we add SMOS, we have a reduction of the standard deviation of the first gas departure, which is good, which is an improvement. And when we were using the SMOS neural network in black, we had an improvement, but with the XGBoost product, we have further improvement reduction in this standard deviation of the first gas departure. It means that there is, when we use SMOS, we have a better fit to 2-meter temperature and humidity observations, which is a really nice independent evaluation. And on the right, it is against radiation temperature. And you see that with the XGBoost product in blue, we reduced as well. Well, we reduced the standard deviation of the departures, which means that we are also in better agreement with the radiation temperature. So it was one application of machine learning to enhance, in this case, it was for SMOS. We've been also working in the context of the CORSO project. So CORSO is a European project which aims at preparing the CO2 monitoring service for Copernicus. And what we wanted to do in this project, so it was completed in December last year, CORSO, it was a 3 year project. We wanted to explore enhancement of the exploitation of the satellite observations in coupled non-atmospheric simulation to constrain not only soil moisture, but also carbon cycle variables, and in this case, vegetation in particular. And when we assimilate ASCAT soil moisture, we only analyze soil moisture. While here, when we use the backscattering coefficient from ASCAT, we have the possibility to analyze simultaneously LAI and soil moisture. So Sebastian Garrigue worked on this, and he developed a forward model, a neural network approach. So on the right, this is again the information content analysis to show which model variables are important to simulate forward the backscattering coefficients, and LAI and soil moisture and soil temperature as well. But LAI and top soil moisture, as expected, came as the most important variables. And so this is the performance of the forward model for ASCAT level, well, backscattering coefficient data assimilation with y-axis the neural network forward model and x-axis the observed backscattering coefficient from ASCAT, and you see a very good performance of the forward model. And what is interesting, so Sebastian implemented it in the IFS, and we did some data assimilation experiments. You see here on the top, it is at the surface, at the bottom, it is in the root zone. You see the comparison of the increments that we have in the soil moisture in 2 experiments. The left one is when we assimilate backscattering coefficients. So we use a neural network forward model so that we can assimilate directly backscattering coefficients. On the right, when we assimilate ASCAT soil moisture, which is what we do still in the operational system. And you see that the structure is very consistent, the sign of the increments are consistent, but we have larger increments. The most important point is that we have larger increments in the deeper layers when we assimilate backscattering coefficients instead of surface soil moisture. And this is due to the sensitivity of the forward operator to deeper soil moisture. And assimilating ASCAT backscattering coefficients brings improvements in terms of gross primary prediction, gross primary product. As you can see on this map, evaluated against the FluxSat dataset. So blue is an improvement when we assimilate backscattering coefficients instead of ASCAT soil moisture. And in particular, high latitudes, we improve GPP when we assimilate sigma 40 from ASCAT. So another activity, still part of the CORSO project, so preparing the CO2 monitoring service for Copernicus. And with a stronger focus this time on LAI, we wanted to explore the idea of using SIF observations in our monitoring service and also for NWP, for both CO2 monitoring and NWP activities. So SIF is really sensitive to this photosynthesis activity. So similar approach, Sebastian developed a forward model using machine learning approach, and you see the performance, so predicted SIF on the y-axis and the satellite observation on the x-axis. Good performance, more, not as sharp as for ASCAT, but still relevant performance of the forward model. And everything is described in this paper. I've put the link here. And data assimilation experiments showed that when we assimilate SIF observations from Tropomi, we improve LAI in particular over crop areas. So this illustrates in blue, it's a LAI root mean square error reduction compared to the Copernicus land LAI. And it's really focused on crop areas, which is very interesting and also very consistent with what the partners in the project have obtained at Météo France in particular with another data transmission system and another land surface model. So beyond ASCAT and SIF and smooth activities, I want to highlight the fact that using machine learning retrieval or observation operators, in the case of coupled data assimilation, we really focus on observation operators to analyze simultaneously several variables. We started also to explore the usage of GNSS-R observations. So it is in the context of an ESA project. So as you know, GNSS-R gets information from the signal which is reflected at the surface, and the wet soils reflect more strongly than the dry soils. And the strength of this approach is that GNSS-R is in fact using existing GNSS, like GPS or Galileo. So it's really an opportunity of information. So there is a low orbit satellite which is capturing the reflected signal. And it provides very frequent observations at higher spatial resolution than the ASCAT or smooth observations. And it is very low cost because it's an opportunity mission. So HydroGNSS was launched in November last year. And we started the project in preparation of HydroGNSS. We don't have yet the data from HydroGNSS. So we use Cygnus, Cyclone GNSS, and two persons are working on this in the team, Eleni Kalogeraki and Yana Kolasa. And in particular, Yana Kolasa, she has developed a forward model to simulate GNSS observations from Cygnus using model features. So on the left, you see information content analysis. So the most important information are related to the geolocation and the orography, vegetation, and soil moisture, as we would expect. And on the right, you see the performance of the forward model, similar plots than previously, with the observation on the x-axis and the simulated forward GNSS on the y-axis, and very good performance already of the forward model. So GNSS-R is complex to simulate, and these statistics really compares very well to physics-based approaches that are the state-of-the-art physics-based model as discussed in the consortium with the partners associated to this project. And this map just compares qualitatively. You see on the left, this is the neural network forward GNSS-R simulated from Cygnus. So Cygnus is in the tropical, well, plus or minus 38 degrees latitude band. This is why we have these limits here. And on the right, this is the target, the observation. And you see that the patterns are very well captured by the forward model. So this is an ongoing activity. It's a 2 years project. And the next steps started to implement the forward model in our land data assimilation system and to assess the impact both on the land surface data assimilation and subsequent NWP forecast. So everything that I said so far is related to our traditional NWP system. So we use observations as input. We have different data assimilation systems for the different Earth system components, as I said at the beginning, and we use a coupled data assimilation approach. So we have data assimilation, and then we have a numerical weather forecast model to issue the actual forecast. So we issue 2 forecasts. Every 12 hours, we issue a 10-day forecast, and we also do sub-seasonal and seasonal forecast. In addition to the traditional NWP system, you've heard and Jon mentioned in the introduction about AIFS, which is a data-driven weather forecasting system, which is shown on the right. So the idea is to have a weather forecast model which was trained on our RNAsys, ERA 5 in our case, but other centers also have machine learning forecasting model trained on other RNAsys like In Germany, they are training their AI model, AI cone on their reanalysis. So the idea is to train a forecast model on the reanalysis dataset using multi-decadal information from the reanalysis and to replace the forecast model by this AIFS model. But this AIFS model still relies on the initialization from the data assimilation. So everything that I said before to improve the initialization of the land surface is also beneficial for the data-driven weather forecast model. And yes, so most data-driven forecasting models are trained on reanalysis dataset, as I said, ERA5 in our case, which is produced as part of the Copernicus Climate Change Service at ECMWF. So this AIFS model, in the first version of AIFS, only the model was trained to reproduce, to forecast the atmospheric variables only. And it was already a big achievement because we could demonstrate at the very early stage of AIFS 3 years ago that AIFS was very good to capture the general circulation and the main atmospheric variables. But very quickly, we wanted to implement land surface variables in AIFS. And on the left, you can see, well, let's start on the right. On the right, this is an illustration of what we have in AIFS, what we've had since February 25, when AIFS version 1 was implemented in operations. We have soil temperature, level 1 and 2, soil moisture, level 1 and 2, but there is also runoff and precipitation, snowfall. So already a few land surface variables. And this illustrates on the left the root mean square error for different lead times, again from day 1 to 10. The red line is the IFS, so as expected, the 2-meter temperature forecast globally, the error increases with the lead time. And for the yellow line is the prototype AIFS version that we had already in real time, but not yet operational, which didn't have land surface variables. It is a yellow line. And when we added in version 1 soil moisture, soil temperature, we could see an improvement, a reduction in the 2-meter temperature forecast, which shows that the AIFS model has really learned from the physical relationship between soil moisture and 2-meter temperature. And this article was just accepted recently, describing AIFS version 1. But while the paper was just accepted, in fact, AIFS version 2 was already implemented in May, before the version 1 paper was actually accepted. And in AIFS version 2, Nina, Raoult, and others, Yuan Pennington, and many others, they've worked on implementing snow cover in IFS, which was really something that was missing in version 1. So we have it now in version 2, which is a great improvement. You see an illustration on the left, a map of snow cover from AIFS version 2. And on the right, you see how useful, how, well, good is AIFS version 2 to represent snow cover. So you have the IMS snow cover from known as this, which is a dashed line. The IFS is a red line, and AIFS is the purple line, which is much closer to IMS in different areas. So East Asia, North America, Europe on the top left, and Scandinavia on the right. So it's a really big improvement of AIFS compared to the IFS itself, because in fact, AIFS is trained on the analysis. It is not trained on the forecast, it is trained on the analysis itself. So it has better performance than the physical forecast in terms of snow. And this presentation is about land surfaces, so I should not talk about the ocean and sea ice, but I wanted to highlight that beyond the land surface activities, AIFS, there are many people working on the AIFS enhancement to represent the surfaces, not only over land, but also over ocean surfaces. AIFS version 2 now includes significant wave height, but there are also ongoing activities to include sea surface temperature, sea surface height. And another paper is on archive from Sarah Hanner et al., which I recommend you to read if you want further details. So yeah, so far we've discussed the traditional NWP system and the AIFS, which AIFS includes more and more land surface variables, which is great, and it also benefits from the machine learning activities that we do on the data assimilation side. But there is another approach that we are exploring, which is AI-DOP, which is DOP stands for Direct Observation Prediction. And the idea is to have an end-to-end data-driven weather forecasting where we remove the dependency on physics-based data assimilation. Because in AIFS, the performance of AIFS, it really outperforms the physics-based forecasting model. In terms of operational implementation, it still requires to maintain both the machine learning AIFS system and the data assimilation system. So it works, it's very efficient, it works very well. It is a bit heavy to maintain in operation. So we are exploring other approaches. It's more on the research side, AI-DOP. So the idea is to train a machine learning forecasting model directly on the observations instead of training on reanalysis or fine-tuning later on operational forecast. So it's trained directly on various type of satellites and in situ observations. So the point is to use historical observations, multi-decadal historical observations to train a neural network to forecast future observations. So the point also, the good thing, the interesting approach here is that it is by design, it is a full Earth system approach. It includes whichever observation we put in the training related to atmosphere, land surface, or ocean. The system doesn't care if it is ocean, land, or atmosphere. It sees observations and it is learning the physical relationship between the different observations. So it is a similar design than for the IFS, except that the input are observations, but there is an encoder, processor, decoder approach. I think there was a seminar earlier this year from Yuan Pennington describing this type of approach. And yeah, again, learning directly a physical model of the Earth system directly from the observations. There are several papers, I've listed two here, but there are many more, and one to be put on archive very soon by Yuan Pennington today or tomorrow or by the end of the week. So this is just one illustration of what AI-DOP is doing. So on the left, you have an illustration of AI-DOP forecast of severity observations. And on the right, it is a severity observation target in the infrared. So you see that the AI-DOP forecast does a very good job to forecast the evolution of the cloud, the structure. You see really the weather patterns very well captured in the AI-DOP forecast. So it is just to illustrate what AI-DOP does. And we also started to wonder, okay, what about the land surfaces and the ocean surfaces as well? What about the surfaces in DOP? Because initially, as for AIFS, DOP was developed purely for the atmospheric variables, but 2-meter temperature was introduced to anchor the satellite observations. So we use satellite radiances from microwave, infrared sensors. We also use radiosondes, which allow the machine learning model to learn the relationship between the radiances and temperature, wind, humidity, pressure. And we also include the sign-up observations at the surface for 2-meter temperature. And here we can see on the left, it is a graph DOP forecast. I think it's a 24-hour forecast, severity for severity observations. And in the middle, you see the temperature and wind forecast from DOP. And on the right, it is the ERA5 reanalysis for the same valid time. And you see that the heat wave, it was sometime in summer 2022, the heat wave that was affecting Europe at that time was very well captured by GraphDOP in terms of 2-meter temperature. So it is not only forecasting the satellite radiances, but also the 2-meter temperature. And another point is that it maintains a good consistency between the wind and temperature forecast, which is very clear when we compare the ERA5 and the GraphDOP forecast. So at this stage, we don't had any land surface or below surface, purely land surface observations in DOP, but we started to explore the idea of including satellite observations in DOP, which are sensitive to soil moisture in particular. And Sébastien Garrigue started to work on this because he was working on sigma implementation of backscattering coefficients from ASCAT in our traditional NWP system. And the idea was to implement sigma 40 as well in the DOP system. So here we see an illustration of what DOP does on 2-meter temperature when we use sigma 14 DOP compared to a configuration of DOP system where we don't have any ASCAT information. So it shows that the 2-meter temperature is reacting to the presence of the ASCAT observations in the DOP system. So the predictors used for this development are radiosondes, so we always use radiosondes in the DOP system, and for satellites, ATMS, AMSUR, YASI, GPSRO, AMVs, and for the surface, buoy, ship, automatic weather stations, plus ASCAT sigma 40. So this is what we wanted to test, and you see that the training period is shorter than for the normal DOP system because it's a development activities, and validation is 21, evaluation 22. So we could see on the previous slide that 2-meter temperature was sensitive to the presence of ASCAT observations over land surfaces. And here we see the impact for lead time 1 to 5, because it's a simplified configuration of DOP, so it goes to day 5. And it is a root mean square error growth of the 2-meter temperature forecast in the southern hemisphere, extratropics on the left, and northern hemisphere on the right. And the blue line is without ASCAT in DOP. And when we add ASCAT, the backscattering coefficients 40 degrees over land surfaces, we see that we slightly reduce the 2-meter temperature forecast in the northern hemisphere, but we slightly degrade in the northern hemisphere. So then we have a bit larger errors. So it is very preliminary results, so almost out of the box, so still to be interpreted. So we are just scrutinizing the results right now. And this is another illustration for the geopotential height at 850 hectopascal. Again, southern hemisphere on the left, northern hemisphere on the right. And here we see that the ASCAT usage in red reduces the errors. So still to be understood, in particular in the southern hemisphere, the impact is very big. But overall, rather positive or neutral impact. And the main message is that AIDOP, the system is learning to forecast ASCAT sigma 40 over land surfaces, and that it influences the upper air forecast. But more work is ongoing to better understand the results. And on the top, you see a prediction of ASCAT sigma 40, because as I said, with DOP, we forecast the observations, so we forecast the satellite radiances, but we also forecast temperature, wind, humidity, pressure profiles, and surface temperature and humidity as well. And you see the root mean square error. So the prediction of ASCAT sigma 40 on the top is, in fact, you see the range of values and you see the errors at the bottom. The errors are very small compared to the range of values. So it makes sense. The prediction of the sigma 40 from DOP makes complete sense. But using ASCAT in DOP without any in situ soil moisture to learn the relation between ASCAT sigma 40 and soil moisture, it's not really useful. Okay, we can predict sigma 40, but and what? So it's not super useful. So the next step was really to include the in situ soil moisture observations. And for this, we've used the ISMN, International Soil Moisture Network, in situ soil moisture in DOP, so that the neural network could really learn the relationship between in situ soil moisture and satellite information, which is sensitive to the surface. So in this case, there is ASCAT Sigma 40 is the main one which is used, but there's also even the sign-up 2-meter temperature. And on the left, you see an illustration of the time series of soil moisture obtained for one of the ISMN site in Europe, and at the bottom, it's another example in the US. And the observation from ISMN is blue, and predicted DOP soil moisture is in red. It is a short-range forecast. But for us, the main we are super excited to see that, because one of the issues that we have in the traditional system is that soil moisture is biased. It's very difficult to have unbiased soil moisture in our model. And by design, DOP is learning the physical relation, and using in situ observations, it is unbiased. And on the right, you see an illustration of when we use ASCAT sigma 40, it is a blue line. We see the growth of 850 temperature forecast errors from day 1 to 5. When, in addition to ASCAT sigma 40, we add in situ soil moisture, we reduce slightly the errors. So it is beneficial. It seems to be beneficial for the atmosphere, but it's very preliminary. The main message is that we are including surface observations, extending the direct observation system to below the surface with a top soil moisture layer. But further work is ongoing, and we are planning also to explore other variables such as snow and soil temperature. And finally, how much time do I have? Not much. Because this AI DOP system is so efficient in terms of computing time, Yuan and others started to test an end-to-end approach, a DOP system for reanalysis applications using various satellites listed here, and a long enough training period. So it is not the latest version, but the training period goes back to 1980 in the current version that we have until 2020. And using a similar approach, encoder, processor, decoder approach. So training purely on historical observations to learn the physics of the Earth system using only observations, and then to use this to produce reanalysis. So it is super efficient. It allows to produce just in a few hours 40 years reanalysis. So less than a day for 40 years reanalysis. On the left, you see an illustration of the global mean temperature anomalies in AIFS DOP for 40 years for different pressure level in the atmosphere. So you see anomalies, blue cold anomalies and red warm anomalies. And at the bottom, it is the same obtained from ERA 5. And well, you see that they are very consistent, not perfectly consistent, but very consistent. One area, interestingly, where they are not perfectly consistent is here around the years 2000, 2005. In ERA 5, there is a cold anomaly, which is not in AI DOP reanalysis. But in fact, this is not the final version of ERA 5. ERA 5 was rerun for that period because there was a bias correction issue in the stratosphere due to implementation of new observations. So it is very interesting that, in fact, now we have an updated version of this plot where ERA 5 is actually consistent with DOP. And on the right, you see an illustration of the 2-meter temperature trend, the anomaly, the trend of the anomaly, sorry. And globally, from ERA 5 in red and from the AIFS DOP reanalysis, it's a 12 months rolling mean. And you see that they are in very good agreement, not perfect agreement, but very good agreement. So this is an ongoing area of research, and a paper is in preparation for this. But very promising results for reanalysis applications. And again, having more land surface, extending the DOP approach to land surface variables, as we started to do for soil moisture, would be extremely useful for future machine learning reanalysis. So just to summarize, first of all, on the traditional NWP system, we've seen that there is a strong and significant impact of land data assimilation on NWP. I illustrated it for soil moisture, but we also have very strong impact of snow. We are developing coupled assimilation to enhance the exploitation of surface observation in our NWP system. And for this, we use machine learning observation operators so that we can use level 1 observations. And our objective is really to analyze several land surface variables, in particular soil variables and vegetation variables, so that our coupled assimilation is not only land atmosphere coupled assimilation, but it's within the land surface, it's coupled between soil and vegetation for the benefit of NWP, reanalysis, and CO2 monitoring applications. And the machine learning forward models allow to enhance the exploitation of the current satellites like ASCAT. We've been using ASCAT for ages, but we want to enhance the usage of ASCAT to constrain vegetation. But it also allows um, to use new observation types that we don't yet assimilate for NWP, like SIF or GNSS observations. Um, and finally, in the last part of the presentation, I discussed the fact that we are working very hard now to include, very actively to include land surface variables in AIFS, soil moisture, soil temperature, runoff, snow cover, and Nina Raoult is working on urban areas and lake implementation. So there is a long list of improvements is, which are in development for AIFS. And we are exploring the potential of end-to-end machine learning approach, such as a graph DOP or AI DOP, which really gives unprecedented capability to exploit surface-sensitive observations for weather prediction and climate analysis. And last slide, I want to advertise this workshop. I'm sure you're aware of it, but you have until Friday next week to submit an abstract if you're interested to submit an abstract. We have outstanding keynote speakers. And yeah, so I invite you to visit this website indicated at the bottom or to take a picture of this QR code. And that's it. Thank you.
Amazing. Thank you so much, Patricia. That was a really wonderful presentation. So now we'll move into the Q&A section. So if anybody in the audience has any questions they'd like to ask Patricia, feel free to either post it in the Q&A chat or to raise your hand and then I can unmute you. We did get two questions during the presentation. The first one, I believe, was while you were discussing the different satellite missions you incorporate. And someone's asked about is it pronounced Aeolus mission, which I think is winds? Maybe you know more than me. Um, I guess the question was maybe whether you have any plans to implement that or whether you've used that.
Well, Aeolus was, it's been used in operations when it was live, but the mission has ended now. And it's really for the atmospheric component. So I would say that it's not something that I addressed in this presentation because it's focused on the atmospheric. It's been very beneficial for the atmospheric forecast, in particular in the tropics, but not related to the land surfaces.
But yeah, great, thank you. And then Francesca Cavella asked, how deep in the soil can ASCAT backscatter inform our knowledge of soil moisture?
Yeah, thank you, Francesca. It's a good question. Well, as a rule of thumb, we say 2 centimeters, but it really depends on the soil moisture and vegetation conditions. So the denser the vegetation, um, the more superficial it is. And this is another motivation that instead, when we assimilate ASCAT retrieved soil moisture, uh, there is an a priori correction for the vegetation effect. But when we assimilate backscattering coefficients, we do account for this in our forward model so that when the vegetation is very dense, our analysis will focus more on LAI increments rather than soil moisture. And in contrast, in areas where we don't have much vegetation, ASCAT will provide more increments to soil moisture and go deeper into the soil if soil moisture is not too high at the surface. So it varies. And it is one of the motivations to have our own forward model instead of using a retrieved product.
Great, thank you. Just to follow up on that, so does that mean there's sort of a spatial bias then introduced if you use the derived soil moisture product there based on, vegetation density or soil types?
Yeah, well, it could, but we do a bias correction. When we use a retrieved
Yeah,
product, we apply a soil moisture bias correction so that the climatology of the retrieved product and the climatology of the model uh, are consistent, and the data assimilation system updates for the small temporal scale variability.
great. Cool. Um, Then Andrew Fox has asked, what is your best guess for explaining the sensitivity of the ASCAP backscatter operator to root zone soil moisture?
Yeah, it's a good question. So it depends on the area, and as discussed before, it depends on the vegetation density, it depends on the soil moisture profile within the soil, and the drier the top layers are, the deeper the signal can go.
Great. Um, Clara Finkel has asked, does ECMWF work on explainable AI? I know I saw you had some SHAP values and feature importance.
Yeah, well, we use the sharp values to really to understand what are the most important features uh, that we need to take into account in our forward model. So it's more to support the development of the forward model.
Do you have any plan? I'll just follow up on that. Do you have any plans to, operationalize it, sort of explainable AI, some of this stuff out of it, or do you just foresee using it more for internal development uses?
Yes, it's more for internal development that we use these tools.
Okay,
But
thank
we
you.
have plans to make operational our, for example, ASCAT forward model in the IFS. We really have plans to make it operational uh, in the not next year, but when it is mature enough, the plan is to have an operational usage of the machine learning observation operators that we've developed.
Great. And then the last question in the chat at the moment is from Hong Zhao asking, will the SMAP TB data also be involved in the DOP forecasting?
Yes, it will be at one stage, but we go step by step because DOP, well, it is in development, and the plan is to progressively uh, all the observations that we use in the traditional NWP system, the plan is really to progressively implement or at least to explore the value of these observations in the end-to-end system. And SMAP is, we have some activities ongoing in the traditional NWP system to activate SMAP data assimilation, in particular over ocean surfaces. And yeah, the plan will be at one stage. We don't have any concrete plan, but the plan is that each observation type that we use in the NWP system, we will dedicate some effort to implement it in the machine learning system.
Great, thank you. I hope that's answered everyone's questions who posted something in the chat. We've still got a bit of time, so I might ask a question I have, if that's okay. I think it was on slide 23 where I saw that the AI dot model uses 12 hours of observations as inputs. I was wondering, how does that compare to sort of the IFS and things? Is that similar? Is it different? Have you tested whether, having more prior information is useful, or yeah, I guess, is it a benefit of the model, or is it pretty typical, these 12 hours of observations?
So in the results that I presented, where we put ASCAT, we use 6 hours, the last 6 hours twice, so 12 hours of observations to initialize AI DOP. But in a more recent version, which is described in the paper from U1 that will be put on archive later this week, which I pointed it to, we use a warm-up over 30 hours. So we use the last 30 hours in the most up-to-date versions of DOP. And compared to the NWP system, in the NWP system, we have 12-hour data aspiration windows. Um, yeah.
Okay. Yeah. And with that extra, 18 hours of data, did you see a big improvement in performance?
Yes. Yes. There are various reasons for which the latest version in Yuan's paper has some improvements. One of them is the extension of the training period to go back to the 1980s. But yes, this warm-up for input observations is also beneficial, but I don't have the number in mind.
No problem. Great. So I think that might be all the questions we have then. So I'd just like to thank you again, Patricia, for presenting to us all this evening. Um, it was a really interesting talk, and I hope everybody. Oh, we have a hand raised all of a sudden, or not? Maybe not. It went up and down very quickly. But yeah, thank you so much for a very interesting presentation. As I said in the Q&A, the slides and the presentation recording will be available on the GUX website. And otherwise, the next meeting or seminar is in July. Um, I think it might be me presenting actually, but it'd be good to see you all there again. But otherwise, yeah, I'd just like to extend the thanks of all of us and Glass, the organizers, to you, Patricia, for joining us this evening. Thank you
Yeah,
very
thank you
much.
very much. Thank you for the good questions as well and good discussion.
So yeah, I hope everybody has a lovely evening, and we'll see you next month. Great.
Bye.
Bye.